Hello. So when I was invited to speak at this meeting, so I thought for a while what a physicist who has been dabbling a little bit into history of science, can talk about. So most of you probably know that that three extraordinary physics discoveries took place in colonial India in quick succession. Shaha ionization equation in 1920, Bohr statistics in 24, and Raman effect in 28. And all these three discoverers, M.N. Shaha, S.N. Bose, and C.V. Raman, they are all faculty members in the newly established physics department of Calcutta University, though Bose had left for Dhaka University before his famous work. And in fact, in the poster of this meeting, it is logically sensible to talk about these three very different discoveries in the same talk. So I would argue that it makes some logical sense because all these three discoveries were in the field of interaction between matter and radiation, a subject which occupied the center stage of physics in the first few decades of 20th century and which gave rise to the quantum revolution. So I plan to talk in this manner. So first I shall present a crash course on matter, then on radiation, then I shall discuss the interaction between matter and radiation before I come to these discoveries. So initially I was thinking of giving some introduction to all these three works. Then I realized that the time will be just insufficient for that. So after giving some introduction to Shaha equation and Bohr statistics, I shall just make a few comments about Raman effect without getting into the details. So first, crash course on matter. So although many ancient philosophers in different countries, including India, speculated that matter may be made up of atoms, so it was only around 1980 that Dalton formulated the modern atomic theory to explain certain irregularities in chemical reactions. So after that, for several decades, atoms were considered indivisible until J.J. Thomson discovered the subatomic particle electron in 1897. So how electrons are organized inside an atom, that question was settled by Rutherford by a very ingenious experiment from which he concluded that an atom is somewhat like a miniature version of the solar system. So there is a positively charged nucleus at the center and negatively charged electrons are going around them. So there is one very big difference from the solar system in which a planet can be at any distance from the sun. But Bohr realized in 1913 that to explain certain experimental data, you have to assume that electrons can occupy only certain specific orbits inside the atom and not any arbitrary orbit. Okay, after this, let me come to radiation. So again, this most obvious example of radiation is light. Again, philosophers have speculated about the nature of light, and Newton suggested that light consists of corpuscles. But in 1803, Young discovered a phenomenon called interference of light, from which it became clear that light has to be of the nature of a wave. And physicists wondered it is a wave in what? And this Maxwell worked out this famous theory that light is an electromagnetic wave, which means that inside light there are electric and magnetic fields oscillating at very high frequency. In fact, in any wave, you have to have something oscillating at very high frequency. So I give some examples, show some sketches of waves of which one has a higher frequency and another has a lower frequency. So for yellow visible light, this frequency has an incredible value of 5 into 10 to the power 14 oscillations per second. and radio waves have a lower frequency, whereas X-rays have even higher frequency than that. So now I come to interaction between matter and radiation. So certainly they do interact. If you hit matter like a piece of iron, then it will give out radiation. And we all know that if you send radiation from the sun through a prism, then it breaks into a spectrum of different colors. And Fraunhofer discovered in 1817 that there are certain dark lines in this spectrum. And then a few decades later, Bunsen and Kirchhoff realized that these dark lines are actually the signatures of various chemical elements, indicating which elements are present in the sun. And although this non-scientists like to see this colorful presentation of the spectrum, so often scientists like to present the spectrum in a sort of a more boring plot, in which you plot the energy associated with a particular wavelength against that wavelength. So in that plot, the spectral lines appear as some dips. And apart from these dips, if you look at the spectrum of the sunlight, otherwise rest of it approximately looks like something which is called black body radiation, which I shall discuss more in the next talk. So keep this in mind, that the spectrum of sunlight is approximately like black body spectrum plus spectral lines. And I may mention that S.N. Bosch's famous work pertains to black body spectra, whereas M.N. Shah's famous work pertains to spectral lines. And here is an introduction to black body radiation. So suppose you make boxes of different metals, iron, copper, or aluminium, and keep all of them at the same temperature, T. And if you make some holes by the sides of these boxes and take a spectrum of the radiation coming out of that, then you will find that spectrum of radiation coming from all these boxes will be identical. So basically inside the box we have radiation in equilibrium with matter, and that is the radiation coming out. And when radiation is in equilibrium with matter, it has a universal spectrum depending on only on temperature, and that is called this black body spectrum. So next I show a plot of this black body spectrum at different temperatures. And quantum theory arose when Planck tried to give an explanation of this black body spectrum, and realized that to explain this, one has to assume that matter emits or absorbs radiation in packets of energy, which are called quantum, and these packets of energy each packet has energy h nu. Nu is the frequency of the wave, and h is now called Planck's constant. And initially it was thought that you have to bother about quanta only when radiation is being emitted or absorbed by matter. But very soon Einstein realized that even when light propagates to space, it propagates in the form of packets of energy, which are called photons. And then Bohr was able to give a proper theory of spectral lines based on his atomic model that atoms have discrete energy levels. So suppose some atoms have two possible energy levels, E lower and E higher. So it is possible that atoms at energy E lower absorbs a photon of frequency h nu, which is just equal to the energy difference between higher and lower levels, and then these atoms go to the higher level. And since such atoms would be able to absorb photons only for having frequency nu, which satisfies this equation, so you will see absorption only at certain frequencies, and that will give rise to spectral lines. And eventually these ideas were further led to quantum mechanics, which I shall not discuss in this talk. So now I come to Shah ionization equation. So what I have written there is the form of this equation as it appears in Shah's first paper on this subject. So after Rutherford established the atomic model, it became clear that under certain circumstances, it is possible for an atom to lose an electron. So here I show a sketch of the simplest atom, hydrogen, which has one electron and has lost it. So this process is called ionization, and this Shah ionization equation gives the fraction x of atoms which are ionized at a particular temperature T and a particular pressure P. And from this equation, one can easily show that as temperature increases, the ionization fraction keeps on going up, and eventually a gas becomes completely ionized, and that is called that state is called the plasma state. So this equation describes the transition from an ordinary neutral gas to a plasma. And Shah also realized that this equation can be applied to solve certain important long-standing problems of astrophysics. So when you look at stars, even with your naked eye, you realize that different stars have different colors. Some appear bluish and some appear reddish. And astronomers found that the stars of different colors have different spectral lines. And since the spectral lines indicate the composition of the star, this raised a very bothersome question. So does this mean that different stars of different colors have different chemical composition? Are they made of different chemical elements? So this problem was solved by Shah when he realized that stars of different colors have different surface temperatures, and because of that they will have different levels of ionization, and that's why they have different sets of spectral lines. Even their composition is the same. So in one stroke he gave a complete explanation of the stellar spectroscopy. So Shah is regarded one of the founding fathers of two important branches of physics, plasma physics and astrophysics. And I quote from the well-known textbook Theoretical Astrophysics by Roseland: "The impetus given to astrophysics by Shah's work can scarcely be overestimated, as nearly all later progress in this field has been influenced by it, and much of the subsequent work has the character of refinements of Shah's ideas." And Shah was nominated for Nobel Prize several times, but these nominations were not successful. So curiously, Shah was one of the three shortlisted candidates for Nobel Prize of 1930, and it happened that C.V. Raman was another of these three shortlisted candidates, and the Nobel Prize went to him. Okay, so now I come to Bohr statistics. So as I mentioned that Planck introduced quantum theory to explain the black body spectrum, but many physicists, including Planck himself, felt that this original derivation given by Planck was not so satisfactory. So the important question was is it possible to give more satisfactory derivation of this black body spectrum? And Bohr was able to give the first such derivation. So how did he do that? So first think of molecules in this air in this room. We know that molecules are all moving randomly with different speeds. So you may wonder, why is it that all molecules are not moving with the same speed? The reason is that the probability is very low that all the molecules would have the same speed. So there is one branch of physics in which one develops methods for calculating these kinds of probabilities. That branch of physics is called statistical mechanics, of which the foundations were laid down by such giants of physics as Maxwell, Boltzmann, and Gibbs towards the end of 19th century. And based on Einstein's work that light can be thought of a collection of photons, Bohr realized that one can view the black body radiation as a gas of photons. So then the the question is that to this gas of photons can one apply the principles of statistical mechanics? But since these photons are quantum particles, one has to do a quantum version of statistical mechanics, and Bohr is the first person who figured out how to do that and gave a first satisfactory derivation of black body spectrum. So he had two achievements. So he could explain the black body spectrum, and he laid down the foundations of a new branch of physics, quantum statistical mechanics. So when Bosch's small paper was rejected by Philosophical Magazine, he sent it to Einstein, a complete stranger to him, with this covering letter asking Einstein whether there is a possibility of publishing this paper in a German journal. And Einstein was so surprised by this paper from a stranger that he himself translated the whole paper and published in Zeitschrift für Physics. And Bosch had applied his statistical method only to particles with zero mass like photons. So, but Einstein realized that these principles can be generalized to other particles with non-zero mass, and when he did that, he was able to get some really remarkable results which were experimentally verified many years later. So anyway, there's many quantum particles like photons obey this Bose-Einstein statistics, and they are called bosons. And other quantum particles like electrons were found to obey a somewhat different kind of statistics, Fermi-Dirac statistics, which are called fermions. And about the impact of Bosch's work in this famous biography of Einstein, Subtle is the Lord, Abraham Pais listed 4 revolutionary works in old quantum theory, and here you see the list. And apart from Bosch's work, the other 3 works all received Nobel Prize. And you all know that Planck and Bohr were towering figures of 20th century physics. These papers happen to be their most important and famous paper. So to have a paper classified with these 3 other works, so there cannot be any higher honor for a physics paper, and probably most physicists would agree with Abraham Pais's list. So yeah, so curiously, Bosch was nominated for Nobel Prize only after 1956, and that also only by Indians. And he was also elected a fellow of Royal Society rather late in 1958, when Dirac was visiting India, and he was surprised to know that Bosch was not yet an FRS, and he took the initiative of nominating Bosch for the Royal Society. So curiously, the name Bosch or boson appears in the citations of several Nobel Prizes, which I have listed here. Okay, so I at last come to Raman effect. As I anticipated, I would not have much time to discuss Raman effect in detail. So let me just make some comments. So quantum mechanics started being developed from around 1925, and what Raman did was to provide an experimental confirmation of a very important theoretical prediction of quantum mechanics. So I cannot go into any details of that, but here I show a sketch of Raman's experimental setup as drawn by Raman himself. And this importance of this work was almost realized immediately, and Raman received the Nobel Prize within 2 years of this discovery. And in fact, I may end with one curious story that Raman was so sure in those days. I think to go to Sweden from India, you have to book a passage in a ship long time ago, otherwise you would not get it. And so So those days, Nobel Prizes were mostly won by Europeans. So Nobel Prizes would be announced only shortly before the prize-giving ceremony. And in fact, Rabindranath Tagore was also not able to attend the Nobel Prize ceremony. But Raman, who was a supreme showman, did not want to miss the ceremony. So he was so sure of winning the Nobel Prize in 1930 that he booked a passage to Sweden well before the Nobel Prize was announced. Okay, I hope that I have been able to give some idea of these three famous physics discoveries in colonial India, and I shall stop here. Thank you.